describe different aspects about the valorization of waste generated in the filleting activities of fish farming species. This presentation is divided in three sections. In the first point, I will establish the problem and the current status of those wastes produced by fish farming industry. In a second one, I will explain the most interesting results that my group have obtained in the GAIN project about the production of valuable biocompounds from agricultural waste. These compounds were fish protein hydrolysates and fish oils, collagen and derivatives, production of fish peptones for microbial uses, and the recovery of biopatites from fish bones. Finally, I will describe briefly the most relevant conclusion of our work. It's well known that one of the most critical challenges for humanity is the production of enough food for an expected population of 9.6 billion people by 2050. In the last 50 years, the global per capita fish consumption was duplicated in concordance with wealthier habits. Until 80s, the production of fish was supplied by wild capture, but fish farming production has increased continuously up to currently around 50% of total fish. For example, in the production of turbot in Europe, only for the period between 1984 and 1988, tons of wild and cultured fish were equal. The figure shows that fish farming was growing with a global sigmoid profile, with an exponential phase between 1989 and 27, and asymptotic trend from 28 to now. Today, the aquaculture production of turbot is higher than 95% of the total turbot produced and consumed in Europe. Although in many countries, fish species are conventionally marketed as a whole fish, fillet presentation are growing year after year around the world. Filleting procedures generate a huge volume of waste. These byproducts accounts in the range of 40 to 60%, depending on the species. They must be management to avoid environmental health problems in fish farming plants or in fish processing food companies. In the case of the Atlantic salmon, it's the most abundant species farmed in Europe. The residues are of 10% of heads, 20.5% of frames and bones, 2% of trimmings, 3.5% of skins, visceras, and for example, 2% for blood. Similar percentages are also found in the industrial filleting of other species as rainbow trout, sea bream, and sea bass. Aquaculture waste contain a remarkable proportion of valuable components, such as high-quality proteins and oils, even minerals, that must be recovered to make fish farming production truly sustainable and efficient. Yeah. These byproducts are currently used for the production of fish meal, fish oil, or silates or biosilates. What is fish silage? Silage is a liquid or dry product resulting from the chemical hydrolysate of fish waste. It's prepared by the addition of inorganic acids as formic or phosphoric acids to the fish substrates until to achieve a value of pH lower than 4 in order to inhibit microbial growth and avoid spoilage. The figure shows this process, the grinding of the fish substrate, addition of formic acid, for example, homogenization of the mixture, liquefaction of waste, and stabilization and packaging of fish silage. When viscera are present in the fish substrate, endogenous enzymes, including in the pancreas or in the pyloric cachea, can be used as biocatalysts for the production of silage. In the case of biosilage, it is a liquid or dry fermented product obtained when lactic acid bacteria are employed as a reagent for the fermentation, hydrolyzing, and stabilization of fish material. In both cases, these products can be applied as liquids or can be dried by freeze drying, spray drying, or fluided bed drying. What is a fish meal? Fish meal is a material, mainly protein, between the weight of this material are from 50 to 75% of protein, obtaining from the crushing, thermal, and drying processing of different fish substrates or fish byproducts. It also contains a variable level of inorganic fraction, depending on the amount of bones present in the waste and the type of separation process. Fish oil is also recovered concomitantly with the production of meals by cooking, pressing, and centrifugation of fish waste. Its quality in terms of omega-3, omega-6 ratio is a function on the fish species processes. Fish meal and fish oils are basic ingredients in aquaculture feed formulation, and the commercial value are directly proportional to the concentration of protein and the quality of oils. Figures shows a scan of fish meal production. Fish meal plants are configured with a cooker, a press filter, a decanter to separate oils and fish wet solids. Oils are refined by centrifugal separators, and the still waters generated in this stage are mixed with previous solids. This mixture is dried, cooler, and grinding to obtain a material, the fish meal, with less than 10% of wet. Comparing both bioproductions, fish meal, fish oil, and silage, I can comment. Fish silage production is simpler than fish meal, since the equipment necessary is cheaper, and also the energy demand and time consuming is lower than fish meal plants. In general, fish meal production is more efficient and viable by increasing the volume of waste to be treated and the size of the processing plants. Fish silage units are more flexible and more adequate to be implementing in location where the volume or seasonal availability of fish byproducts is not enough to justify operation in a traditional fish meal plant. Silage contain more than 60% of water, forcing an intense concentration or exhaustive drying if this material wants to be marketed far from its place of production. Fish meal production is well established and economical, very profitable business, but other valorization process in line with circular economy principles have been explored in game project. Based on the concept of marine biorefinery, in game we have developed and optimized a set of different processes, chemical and physical, and bioprocesses, enzymatic and microbial, for the valorization of aquaculture byproducts. This sustainable approach was directed to obtain high added value biocompounds and zero waste emissions. Thus, from heads, trimmings, and frames, we have produced fish protein hydrolysates and fish oils that can be applied in the formulation of animal feed, chemicals, or nutraceuticals. From skins, we have recovered collagen, gelatins, and collagen hydrolysates of potential interest in food, pharma, cosmetic, nutraceutical, or nanotechnology devices. Using heads, viscera, trimmings, and frames, we also produce fish peptones, useful as ingredient for biotechnology fermentations. And finally, from skeletons, the bones, biopatites were recovered. Start with our approach to the biocompounds. The first case, what is a fish protein hydrolysate? It is a substrate rich in proteins, peptides, and free amino acids obtaining from total or partial hydrolysis, digestion of whole fish or fish byproducts, as skins, heads, viscera, trimmings, etc. Fish protein hydrolysis, or FPH, can be obtained by using chemicals or enzymes as proteolytic agent. Depending on the quality of hydrolysates in terms of protein concentration, biological activities, molecular weight of proteins, etc., they can be used as nutraceutical, as ingredient of aquaculture feed, microbial growth media, and so on. FPH are classified in terms of the kind of the proteolytic reagent used. So we have alkaline hydrolysis, sorry, when alkalis has sodium hydroxide is used. Acid hydrolysis is obtaining when fish substrates are treated by acidic solutions, has sulfuric acid or formic acid. Commonly, the acid hydrolysate of fish viscera is also known as fish silates. Enzyme hydrolysis is the most interesting and is produced by the catalysis of an exogenous enzyme. The pros and cons between them. Acid and alkaline hydrolysis are cheaper and easier to perform than enzymatic one, but they are difficult to control if you want to produce peptides with tailored size or high biological activities. Acid and alkaline mainly produce free amino acids at the end of the process after 1 or 2 hours of hydrolysis. They produce bad odor and taste. In game, we focuses on the FPH performed by endogenous commercial enzymes. Protease, also known as peptidase or proteinase, are the specific enzymes that breaks the peptide bonds of proteins to generate polypeptides of different size and even a portion of free amino acids. Proteases are hydrolytic enzymes classified as endopeptidase or exopeptidase. Endopeptidase breaks of non-terminal amino acids break down inside the protein molecule. And exopeptidase breaks at the end of the protein chain, releasing amino acids. Another classification of protease is based on the reactivity of the catalytic amino acid present on the protease. So we have aspartate protease, metalloprotease, serine protease, etc. In the picture on the right, you can observe one mechanism of breakdown of peptide bonds. The insertion of a molecule of water into peptide bond catalyzed by an amino acid of the protease, for example, as aspartate or glutamate, is the cause of the final release of two reaction products. Between enzymes, we find out different commercial proteases depending on the origin, the range of pH and temperature of proteolytic activity or the specific substrate to catalyze. For example, papain is an endopeptidase isolated from papaya, bromelain from pineapple, trypsin from digestive system of vertebrates. The selection of one of another protease is dependent on the pH, temperature, type of break, type of protein of substrate. For example, if you need to hydrolyze at low pH, you should employ the pepsine because it works at the pH between 1.5 and 3. If you want low temperature, choose pepsine, but for high temperature, use, for example, papain or alkalase. If you want to break elastin fibers, use elastase, or if you want to break collagen, use collagenase. In the present studies, we have used alkalase due to his high proteolytic activity, its excellent efficiency and versatility to hydrolyze and digest different fish substrates, as cartilage, skeletons, muscles, etc. And because it is a cost-effective enzyme. Alkalase is a subtilising A, is an endopeptidase produced by a bacteria called Bacillus licheniformis. Now, I will talk about optimization of hydrolysis. The main independent variables to control the process of enzyme hydrolysis are pH, temperature, solid liquid ratio, enzyme substrate ratio, agitation, and time of hydrolysis. These variables are dependent on the type of substrate and the kind of protease. The dependent variables, the response to quantify in a study of optimization are degree of hydrolysis, total protein, yield of digestion, bioactivities, etc. Our strategies to optimize FPH production are displayed in the bottom figure. The first step is to study the simultaneous effect of pH and temperature by second-order factorial design, combining with a kinetic perspective, and the constant agitation, constant solid liquid radio, and constant alkalis concentration. And after response maximization of pH and temperature, these variables remain constant, and protease and the concentration of protease is studied. This experimental design for the optimization combines two approaches: response surface methodology, jointly with modeling kinetic data of hydrolysis to the Weibull equation. After statistical analysis of the results by the student F. Fisher test, polynomial and nonlinear equations permit the analytical and numerical search of optimal conditions that maximize proteolysis process. What are the experimental systems to carry out those studies and to produce hydrolysates? We use thermostatic glass jacket reactor working as pH stat mode. In pictures on the right, three types of pH stat reactors are shown. I showed a 100 milliliters pH reactor using for the optimization, a 5-liter pH stat reactor using for the first scale-up of the process, and a 300 liters pH stat reactor for pilot plant production. They are equipped with systems of agitation, temperature control, and pH control by means of a pH sensor. The sensor is connected to a pump for dosing acid or alkali in order to maintain the pH control previously established. They are also controlled by a specific software for the online monitoring and recording of the mentioned dependent variables. In game, we have optimized the production of FPH from different ways of 5 fish farming species as turbot, salmon, trout, sea bream, and sea bass. As a sample, the production of pH from rainbow trout heads by alkalis is shown in the graphics represented in the figure below. Surface response and histograms are a representation of the joint effect of for pH at temperature, together with the solid liquid radio and alkalis concentration influence. Besides, on the right, the kinetics of hydrolysis in each condition of the factorial plan were modeled with the Weibull equation. Using this combined approach, we could obtain the experimental condition that maximize the production of aquaculture hydrolysates. The values for each variable and species are summarized in the table. Optimal pH were ranged between 8.2 and 9.0. The intervals of temperature were from 56 Celsius degrees to 64 Celsius degrees, and the concentration of alkalis varied from 0.1 to 0.2 volume per weight percentage. The flowchart of pH production for all fish substrates was the same. A first stage of crushing, followed by the enzyme treatment under the previous defined conditions, the separation of clean bones by filtration, the separation of oils from raw hydrolysate by centrifugation, the thermal inactivation of raw FPH, the concentration and drying of the liquid hydrolysate, and the vacuum packaging and cold storage of pH. The pictures show steps of these flowcharts: head of salmon, salmon head grinded, proteolysis of salmon heads inside of the reactor, clean bombs, fish oil, and the hydrolysate pack. Regarding the chemical characteristics of this bioproduction, summarized in the table on the left, we get the almost complete digestion of solid substrates to liquid FPH, a remarkable production of soluble protein, the complete separation of bones and high recovery of oils, highest degree of hydrolysis for turbot, trout and salmon, excellence in vitro digestibility in all cases, and high proportion of essential amino acids. For the oil recovered, observed table on the right, oleic acid was always the predominant fatty acid, followed by linolenic acid. Low levels of eicosapentaenoic acid and docosahexaenoic, except in sea bass oil and mainly in sea bream oil. The values of omega-3, omega-6 ratios were low. These oils are interesting for food and feed supplements and chemical production, but low potential for nutraceutic application due to the low omega-3, omega-6 ratio. Regarding chromatographic profiles for calculating the molecular weight of peptides present in FPH, the molecular weights of peptides were mainly lower than 3 kilodaltons. We found a prevalence of molecular weights in the range of 0.5 to 3 kilodaltons. Average molecular weight for all species and substrates was around 1.2 2 kilodaltons. The number average molecular weight for all species and substrate was in the interval of 0.8 to 1.2 kilodaltons. And taking into account this data of aquaculture FPH, this FPH have a high potential to be incorporated into aquatic diets as substitute of fish meal. The in vitro activities of this FPH, in general, the antioxidant activities were not particularly noteworthy, being salmon FPH slightly higher than the rest of FPH. However, remarkable antihypertensive activities in terms of the percentage of inhibition were found. And FPH from turbot viscera showed the major antihypertensive inhibitory value. For the scaling up of FPH production, we have utilized our pilot plant facilities from IIM CSIC. The pictures show the different equipments employed. A grinder for the crushing and homogenization of raw materials, reactors of hydrolysis in the mode pH state reactor of 300 liters of capacity. Tricanter for the centrifugate separation of solids, FPH and oils. Vacuum evaporator for the essential step to reduce the volume of liquid hydrolysate before drying. And finally, the drying can be done by spray drying or fish drying. Finally, the mass balance of FPH and fish oil production from, for example, 100 kilograms of salmon heads, we can to obtain finally recover up to 11 to 12 liters of fish oils among 11 to 12 kilograms of wet bones and around 12 kilograms of dry FPH. Another production study in game project, the collagen and derivatives. What is the collagen? Collagen is the most important fibrous protein present in animals. It's produced by fibroblastos. Collagen is the most abundant extracellular matrix protein of different tissues, as skins, bones, and connective tissue. Collagen is a supramolecular and fibrillar structure, is insoluble in water, providing structure strength and flexibility to the tissues. The basic structure, the monomer, or called has tropocollagen, presents a right-handed triple helix formed from 3 left and the alpha chains. Glycine, proline, and hydroxyproline are the predominant amino acids in collagen. There are defined at least 21 types of collagens, and type 1 and type 2 are the most abundant in fish. The gelatin is formed after the partial hydrolysis of collagen. Collagen hydrolysates are obtained by enzymatic hydrolysis of native collagen or the gelatins. Collagen, gelatin, and collagen hydrolysates are compounds with multiple applications in different sectors, such as pharmacology, cosmetics, food, nutraceutics, or even tissue regeneration. As example, the flowchart describes the extraction of collagen from salmon skins. All the stages were performed at 4 Celsius degrees. The first step is the alkaline treatment with sodium hydroxide. The second one was the defatted of the skins using butyl alcohol. Next, the precipitation of collagen by acetic acid is the most important step of this treatment. Next, we filtrated the precipitates. We repeat this procedure 3 times with the skin remains. We purified and precipitate the collagen in saline solution. We perform exhaustive dialysis of saline collagen, and the final step for the production of acid-soluble collagen is drying by lyophilization. The yield of extraction was high, and the quality of collagen was excellent. Electrophoresis yield show the characteristic bands for alpha 1, alpha 2, and beta chains. This structure was also confirmed by gel permeation chromatography. In GAIN project, different strategies were studied for the production of gelatins from salmon, turbot, sea bream, trout, and sea bass skin byproducts. In all cases, skins were cut on portions around 5 per 5 centimeters. Skins were initially water washed to eliminate impurities. Then a set of chemical treatments combining alkaline, acidic, or saline washes were applied to the skins before extraction steps. We also studied these procedures at 2 temperatures, 4 and 22 degrees. Skins chemically treated were processed by aqueous thermal extraction at 45 Celsius degrees for the release of gelatins to the aqueous phase. In parallel, a procedure dealing with acidic water using phosphoric acid at pH 5 was also studied. All alternatives were finishes with a stage of purification and deodorization of gelatin solutions by absorption in activated carbon. Finally, gelatins were drying in a forced convection oven. From all those procedures studied, the protocol selected was based on several sequential stages represented in the flowchart. Alkaline treatment at 22 Celsius degrees, sulfuric treatment at 22 Celsius degrees, citric acid treatment at 22 Celsius degrees, the thermal water extraction at 45 Celsius degrees of the gelatin solution, the purification and deodorization by absorption in activated carbon, and the drying of gelatin sheets by forced convection oven. The best extractive yield were found in the following order with the skins of sea bream, sea bass, and turbot. The gels formed with the gelatins of sea bass, sea bream, and turbot showed the highest strengths. The largest content of proline and hydroxyproline were also obtaining in gelatins of sea bream, sea bass, and turbot. In line with the concept of circular economy, and in order to achieve zero waste, the rest of skins were digested by two proteases, alkalase or papain, at 2 times of hydrolysis, 2 or 4 hours, under optimal conditions for the production of these collagen hydrolysates. In all cases, the kinetics of hydrolysis degree were perfectly modeled by Weibull equation. Largest values of hydrolysis degree, soluble protein and essential amino acids were obtaining in alkalase digestions, being 4 hours the best option. In concordance with this result, lower molecular weight of protein were found at higher degrees of hydrolysis. The antihypertensive activity of collagen hydrolysates generated by alkalase at 4 hours were remarkable. So this bioproduct may be an adequate ingredient for nutraceutical formulations. In terms of gelatin production at pilot plant scale, starting with 100 kilograms of aquaculture skins, after the chemical treatments and the thermal extraction, around of 60 kilograms of skin byproducts can be used for collagen, for the production of collagen hydrolysates. On the other hand, the gelatin solutions led, for example, to 6.6 kilograms of sea bass gelatin or 4.7 kilograms of salmon gelatin, depending on the species employed. In this case, it's important to comment that for reducing production costs, the step of charcoal absorption must be replaced by ultrafiltration, the filtration methodology, and the drying stage must be done in a drum dryer, working in continuous mode. Besides, we are now studying the depuration and valorization of acid and alkaline effluents generated in chemical skin treatments by means of microbial bioconversion. Another bioproduct from aquaculture byproducts. What is a peptone? It is a substrate based on proteins composed by peptides and polypeptides of varied molecular weight, including free amino acids and a small concentration of nucleotides, carbohydrates, and lipids. Peptones are water soluble, not thermally coagulable, and are obtained by acid, alkaline, thermal, or enzymatic hydrolysis of raw materials. The name of peptones refers to the origin of raw materials or the enzyme used for producing them. For instance, gelatin peptone is obtained for the pancreatic digestion of gelatin and reaching glycine, proline, and hydroxyproline. In the case of meat extract, is produced from bovine waste. Peptones are the most important and expensive source of organic nitrogen in the microbial culture media. For example, for the microbial production of antibiotics, chemicals, or biopolymers, more than 30% of production cost, in some cases achieving until 80%, are due to the peptones needed in the corresponding fermentation media. In the case of marine or fish peptones, they are peptones generated specifically from fish and seafood byproducts, discards, and effluents. Being aquaculture peptones, those peptones obtaining from fish farming waste. The types of peptones obtaining by acid or alkaline digestion of marine substrate using alkalis or acid reagents, by enzyme digestion using endogenous or exogenous protease, or by thermal extraction when an autoclaving process is applied to fish substrate water mixture for protein extraction from solid to liquid phase. In the present project, we have explored the production of peptones by enzyme digestion and thermal extraction. The scheme of peptones production is displayed in this figure. For enzyme digestion alternative, the process is similar than for the production of fish protein hydrolysate, but including an additional stage of autoclaving and avoiding the drying step. We have used 3 ways: head, streams, and viscera, 5 aquaculture species, trout, turbot, salmon, sibling, sea bass, and 2 types of processing. We have produced 13 peptones. All these peptones were evaluated as organic nitrogen source for the growth of 3 kinds of bacteria: 2 lactic acid bacteria, 2 marine probiotic bacteria, and 2 ubiquitous bacteria. In table, I summarize the main results for fish peptones obtaining from aquaculture byproducts. For all species, the yield of protein recovered from enzyme hydrolysis was higher than those achieved by thermal extraction. In all situations, the concentration of total sugar was lower than 2 grams per liter. The average molecular weight of the peptides present in peptones from enzyme hydrolysis were around 100 to 1,800 daltons, with 5% of peptides larger than 3 kilodaltons. However, peptones from thermal extraction showed proteins ranked mostly between 50 and 614 kilodaltons, since no specific protein hydrolysis was applied in this case. Regarding the applications of fish peptones to the growth of lactic acid bacteria, we have used 2 lactic acid bacteria, Lactobacillus brevis and Lactobacillus plantarum. They are bacteria of high importance for his technological properties. They are probiotics, starters of cheese and yogurts, and lactic acid producers. We use a commercial MRS medium as control. This medium is formulated with glucose, mineral salts, and 2 peptones, mitostrat and bactopeptone. We prepared low-cost media based on MRS, but substituting those 2 peptones by fish peptone at the same level of soluble protein. Fermentation were run in batch cultures at 30 Celsius degrees, continuous shaker, and without supplementation of oxygen. The production of biomass as dry weight were similar or higher in media formulated with fish peptones, but than observing in commercial control media. Similar growth as viable cells were obtaining in all media tested, including control media. Similar production of lactic acid were also found in all media tested. Largest production of acetic acid were observed in media containing trout peptone from thermal extraction. Highest productive yields, growth, and metabolite production per nutrient consumptions were obtaining in media formulated with salmonid peptones. And the most important, from economical point of view, the reduction of production costs using fish aquaculture peptones in comparison with MRS media was of 4 times in biomass, 3 times in lactic acid, and 3.5 times in acetic acid. For the case of marine probiotic bacteria, Phyobacter sp and Pseudomonas fluorescens, we have replaced the commercial marine medium by filtered seawater, yeast extract, and fish peptones. Higher or similar production of biomass as dry weight were obtaining in media formulated with fish peptones than observed in commercial medium used as control marine medium. Similar growth as viable cells were obtaining in all media tested, including marine medium. Highest growth yields were found in commercial medium. This efficiency was also greater for peptones obtaining with enzyme hydrolysis than obtaining with thermal extraction. The reduction of production costs using fish peptones in comparison with commercial marine medium was around 70 and 150 times for both types of growth quantified, both biomass and cells. In the last case, for ubiquitous bacteria, Bacillus subtilis and Staphylococcus epidermidis, the commercial tritone soy broth was reformulated without calcitone and soy peptone and inserting fish peptone. The production of biomass in those alternative peptones were slightly lower than found in commercial medium. Similar or slightly lower growths were defined in fish peptone media in comparison to TSB. Larger growth yields in commercial media. This efficiency was also greater for enzyme treatment than for thermal process. Finally, the reduction of production costs using fish peptones in comparison with TSB medium was around 16 to 26 times for both types of growth quantified as biomass or as viable cells. Finally, we also worked with the non-digested material obtaining after alkalase hydrolysis of aquaculture heads and frames. They were mainly rest of skeletons, bones, composed majoritarily via mineral inorganic fraction of calcium hydroxyphosphate and similars and an organic fraction, protein. The characteristic of this protein fraction in terms of amino acid content for farming species were more than 21% in bones with R protein, reached 41% in the case of sibrin. Glycine, proline, and hydroxyproline are the most abundant amino acids in this protein fraction of the bones. In all cases, the sum of proline and hydroxyproline is higher than 70%. This indicates their potential source for the production of collagen. The bones were used as substrates for the production of biocompounds. Firstly dried at 105 Celsius degrees and crushed, and later on calcinated at 750 Celsius degrees and 915 Celsius degrees using a specific gradient of calcination. The presence of calcium and phosphorus has main mineral components in salmon samples, for example, was determined by energy dispersive spectroscopy. Image of scanning electron microscopy revealed porous-shaped structures without significant difference between the two temperatures of calcination. Granules of irregular morphologies can be also found in the powder samples of salmon bones. We also compare patterns of X-ray powder diffraction of commercial synthetic hydroxyapatite and tricalcium phosphate together with samples of salmon. And this comparison indicates that even though hydroxyapatite was the major component of the resultant powders, there was a small amount of tricalcium phosphate. Other chemical elements were quantified by inductively coupled plasma optical emission spectroscopy. And for all aquaculture bombs, the presence of magnesium and potassium was very remarkable, as well as the level of selenium. All heavy metals analyzed, mercury, lead, and cadmium, showed values much lower than the maximum legal concentration. And the molar calcium phosphorus ratio was quite similar in all samples is also identical or slightly higher than that of stoichiometric hydroxyapatite. In summary, we have obtaining biogenic calcium phosphate, biopatites, from aquaculture bombs containing a biphasic material hydroxyapatite tricalcium phosphate of potential application in organic bombs in plants. They are also doped by other elements, as magnesium, and potassium, etc., which are very beneficial for bone metabolisms and cell adhesion if aquaculture biopatites are used in the formulation of tissue regenerative scaffolds. It is also a substrate of potential use as absorbent ingredient of fertilizer or has a food supplement rich in calcium and phosphorus. Finally, the set of conclusions. In game project at the IIM CSIC, we have developed different strategies for the valorization of aquaculture byproducts beyond the well-known fish meal and silage production. The production of fish protein hydrolysate of quite high quality in terms of protein, amino acids content, digestibility, molecular weight from different ways of 5 aquaculture species have been optimized. Fish oils were also recovered in the same productive process. Various of these FPH were also produced to pilot plant scale in order to be applied in the formulation of aquaculture feeds, replacing fish meal. A protocol for the extraction of native collagen soluble in acid from salmon and turbot skin waste was established. A sustainable process was also developed for integral valorization of skin waste of 5 aquaculture species, yielding the joint production of gelatin, adequate for food and pharma applications, and collagen hydrolysates of potential as a nutraceutical. 30 fish peptones were obtained from different fish farming species by products and types of production. These peptones were successfully employed as organic nitrogen source for the growth of several bacteria of technological interest. Additionally, various of those peptones were also validated for the industrial production of commercial human probiotic bacteria by the biotech company called Biolactics. Clean bombs recovered from the production of aquaculture FPH were studied as sort of valuable biopatites with potential utilization in bone tissue regeneration, supplements rich in calcium phosphorus, and even fertilizers. And thanks a lot for your attention.